Will, who are you?
Well, I do quantum stuff and all related things. So I've been working on quantum technology for the last 15 years or so in a bunch of different ways in academia and startups. I've worked on theory, I worked on algorithms, as well as building systems. Today I do two things, well, two and a half. Um, the first is I'm a partner at a venture capital firm called Quantonation, and we invest in weird physics and weird computing companies. So we invest in a lot of quantum technology things. I'm also the founder and president at a nonprofit called the Unitary Fund, which some of you know, we'll talk about more. And we work on public goods in quantum technologies, so a lot of open source work. And then the other half is I do research too. And the major research areas that I mostly work on are in quantum algorithms and architectures for quantum computing, and then some stuff in quantum information and foundations. So yeah, broadly, I'm really excited about the things that we can do with quantum mechanics at a technological level. And I try and help make that happen. If it can make money, that goes to the fund. If it can't make money, it goes to the nonprofit. And if it's a crazy research idea, it's research. So that's sort of how things break down.
That's awesome. So, Will, something that I was wondering when looking at a little bit into the things that you have done is how you went. It seems from like your trajectory seemed to go from like more perhaps abstract mathematical stuff during the PhD. Correct me if I'm wrong, yeah. But and then slowly towards more applied in the in at Rigetti in the startup, and then now even more towards applications, even tools and stuff. So I was wondering what has been your drive and how have you been developing your motivation for quantum during your trajectory?
Yeah, I'd say the trajectory has been a little bit more oscillatory rather than like narrowing.
Okay.
So often I say like a lot of my career has been oscillating back and forth between what I see as the two big questions for quantum technology, which are how do we build it and what do we do with it? Um, so I kind of started on the how do we build it side, working on superconducting qubits. My PhD's in algorithms, so what do we do with it? Then I went back to building it. Then I went back to work on the finance side and how do we apply advanced computing technologies. And now I'm sort of working across both of those questions at the same time from the nonprofit
Mhm.
for profit funding perspective. And then I guess like along the way, and we can talk about this a little bit more. I mean, my main interest in this field, and one of the things that attracted me to it really early, is that you can do two things at the same time. Uh, don't make the superposition joke. But it's that you get to work, like quantum technologies is about, you can make technologies that could be very impactful economically, in terms of solving big and important problems, can change how the world works. So that's special. But at the same time, the questions you deal with in quantum information are very fundamental. Like, what's the relationship between computer science and physics? And there's interesting questions that come up there. And a lot of the really exciting stuff in physics in general right now, I think, is getting inspired by stuff from quantum information. And so getting to do very applied and very foundational stuff at the same time is kind of special. And that's what attracted me really early on to the field of quantum information and technologies, and continues to be
Mhm.
pretty rich.
Cool. Very nice. So what is, since we are almost already talking about it, and for the people that have less of a background in quantum, what would you say, how would you describe what quantum computing is?
Well, yeah, so
And
it's not just
how it's different? Yeah, sorry,
yeah,
go
so there's
on.
quantum computing, but there's kind of broadly just quantum technologies. Maybe I'll start with that one. So,
Okay, sure.
you know, I think the fundamental limiter for technology that we have is our understanding of physics. It's the rules of the world, and our ability to make use of the rules of the world to do things that we want is called technology. And we've known about quantum mechanics for 100 years. And if we didn't know about quantum mechanics, then there's a bunch of tech that already wouldn't exist. So lasers, transistors, like lots of stuff that we use every day, depend we designed and discovered because we understood quantum mechanics. But only in the last, let's say, 15 years or so-ish, have we gotten good enough to exploit some of the even weirder features of quantum mechanics at a more sophisticated level. So these are things you might have heard about called superposition, or entanglement. There's other kinds of features of quantum mechanics that are very unintuitive. And in some ways, we've had to avoid them because they can be bugs. But in other ways, you can think of them as features and try and make new technologies out of that. And that's what we call quantum technologies. And the broad categories are things in sensing, networks, and computing. And in computing, for example, you really rewrite the basic way of doing computing with different rules. So the fundamental unit is no longer a classical bit that could be 0 or 1. It's now a quantum bit or a qubit, which is described mathematically in a different way. And we can talk more about that, but you can have superpositions of 0 and 1 at the same time. You can entangle quantum bits, which means you can make correlations between them that you couldn't make with regular bits. And that unlocks new algorithms and new speedups.
Mm-hmm. Cool. And what do you think? I always have troubles explaining to other people that are not physicists why quantum is different or what's the special thing about it. And I was wondering how do you go about that, or maybe ask differently, what do you think is the thing that is most often misunderstood, or that stands in the way of really grasping what it is?
Well, in the computing context, I think people don't, well, there's something special about quantum computers compared to other ways of doing computing. And, if there's one thing that the boom in AI stuff these days is telling us, it's that humanity has a maybe unbounded desire for computing power. Like how much compute we want is just, and we think that we're going to want in 10 years or 20 years, just keeps going up and up and up. And Moore's law, depending on how you think about it, is slowing down, or at least at some point it's going to slow down. So what are the alternatives? What are the different things we could invest in? Special processors for specific problems, analog chips, logical computing. I don't know, and quantum computing. There's all these things we could think about ways to make computers faster and better. But among all those ways of thinking about making computers faster and better, quantum computers stand out. And they stand out because the underlying physics that you use is different, which means that you have access to what we call in theoretical computer science a different complexity class. It means there are algorithms that you can't run on special purpose ASICs, no matter how fast they get. That you can't run on biological computing, even if it works at massive scale. There are just entire classes of algorithms that are only accessible if you get the rules of quantum mechanics in your computer. And some of those algorithms offer really, really, really big speedups over anything that we know classically. And that's special. There are, in some ways, if there's no other rules of physics that we could be exploiting. Now, there are a few people who think about like relativistic computing and computers near black holes and that kind of stuff. So there's a little there's a little asterisk there. But it's really at some point, quantum physics is the next thing to exploit for computing. It's going to unlock really new types of algorithms you couldn't run on other ones. And so that's one of the things that makes it very special.
Daniel, you want to ask something?
Yeah, I'd love to just jump in there if it's okay.
Yeah, for sure.
So I think that the example of like specialized chips, graphics chips becoming essentially AI chips, that makes sense to me in the current realm of possibilities. Is there something that if I could put a quantum chip or a quantum board into my computer today, assuming all the technology works, what would that enable me? Like, what's the use case that people are most excited about in 10 years from now when this technology is available to everyone? Like, or is that still sort of the other side of the coin of figuring out the technology is actually understanding the use cases maybe that's
so
there.
There's a bunch of work still going on, and there are use cases that we understand now. The hardest question is like, how good of a quantum computer do you need for certain use cases? But let's just say you have a very big, very good quantum computer. What are you going to be doing with it? There's a few things we know are interesting. One is simulating physics. So, for example, simulating quantum mechanics in particular is hard. And so if you are trying to understand some physical system, like, let's say you're doing something interesting in fusion, or you're doing something interesting in quantum chemistry or material science, trying to design a high temperature superconductor or some other kind of quantum correlated material, then that's difficult on normal supercomputers, even though we spend a lot of money trying to do it. But it's actually something that quantum computers are good at. And so one of the things you'll use your quantum computer for is to design physics systems, to design molecules or materials for some application that you have. And that ranges from things in pharma to chemistry to battery tech, stuff like that. Other areas that people are interested in are in kind of big buckets. So another one is in optimization. So there's some algorithms that we know are faster on quantum computers. And the question is when do those become practically important? There's often an issue of if you had a quantum computer that had the same number of quantum bits as we have regular bits in a regular computer, then yeah, we just run the quantum algorithm. But quantum bits are a lot more expensive than classical bits today. So there's some kind of trade-off point. And in optimization and in machine learning applications in particular, that's kind of a question. But there are algorithms we know that work better for those use cases. And then the last bit is the thing that kind of kicked off everybody in the early 90s to get worried and excited about quantum computing, which are the cybersecurity applications around factoring. And that's something that everyone should be aware of. And and we know that if you have a big enough quantum computer, then you can break RSA, for example, which is not a great commercial application. It's not the one I'm most excited about, but it's definitely one that shouldn't be ignored. We can talk
Nice.
more.
Yeah. Yeah. I'm gonna ask a couple more questions, and then, but at any time anybody can, of course, chip in, like Daniel. I thought maybe I'd ask you about some of the things that you're doing, and specifically we can start with your work at Unitary Fund and open source stuff in general. Like maybe just broadly, why is it important? Why is it important to produce open tools, and what can we do in this way that we can't do otherwise?
Yeah, so, well, I think someone here mentioned they're interested in quantum stuff because it's interdisciplinary, and it's early stage interdisciplinary field, which means there's a lot of gaps. I mean, it's very interdisciplinary. So I did my PhD, there were 5 departments that did quantum information stuff: material science, physics, philosophy, computer science, and mathematics. And we all had more in common with each other than we do with each of our departments, which is kind of neat from an intellectual perspective, but it's difficult from a gathering resources or hiring people kind of perspective. And so in academia, there are gaps in this field. Another gap is that a lot of the work has been very scientific and foundational, and that work should continue, but there's more applied work that needs to happen. Like, we have electrical engineering departments, we have mechanical engineering departments. One day we will have quantum engineering departments, but we don't quite have them yet. And so you can ask, well, why don't companies do this more applied technology focused work? And sometimes they can, but that's only when they're commercially fundable, they're venture backable, and some things that fit that mold are great. I invest in those things, but there's other things in between. So there's things that are not academic papers, but also not companies, that are very important. So examples are standards, compilers, educational materials, Stack Overflow question and answer type websites, benchmarks, like all this kind of glue that exists in regular technology fields or in other fields that you can call public goods. So things that everybody needs, but it's hard to capture value from. And in quantum tech, if we build those things, then it's going to help the whole field get going faster. And so Unitary Fund's mission is to help build those things, but build them in 2 particular ways. So one is to help build them openly so that things happen faster. And second, the other reason we help build them openly is we think by making the field more accessible, we'll get to more important benefits than if people are building them in a closed way. And the simple idea here is in some ways, quantum technology is a hammer looking for nails. And if more people with their different problems are looking at this technology more accessibly, then it's more likely we're going to find useful and beneficial solutions to it, to apply the technology. So at Unitary Fund, our approach, we do it in different ways, and I can talk more about it, but a general approach is by making the field more legible and open and accessible, then it's going to scale faster and better.
Cool. I like how you make my questions better with your very nice answers. I was wondering if there is something in the field of open source development that particularly excites you, that you are particularly interested in. Yeah.
In quantum right now?
In quantum, yeah, in quantum.
Sure. Yeah. Well, I'll list a couple things. So one is for a while. So one of the things we do at Unitary Fund is we have a microgrant program, and we fund a whole bunch of different projects, different parts around the world. We funded people in more than 26 countries. Just hit 100 projects last couple of weeks, and we started to see a bit of a shift. And one of the shifts we're starting to see is folks are looking to fund what we would call like open quantum hardware. So in quantum technologies, let's just say, right now, let's just think about quantum computing. There's a whole stack that you need to build. And from the bottom up, it's sort of parallel to, but different than the classical computing stack. So you have fabrication of chips, or there's different technologies, basically the basic hardware, then there's the microcode on top of that, then there's like assembly, then there's compilers, then there's intermediate representations, then there's higher level languages and applications. And for a while, we've been seeing a fair number of open source projects in the maybe pure software layer. So like compiler technologies, applications, libraries, and stuff like that. And there needs to be more open source there. There needs to be more stuff that's great. More recently, there have been more open projects at the lower levels. So let's think about things like software for helping you design chips, or software for programming control electronics that actually send the signals to the quantum computer that you're controlling. So like there's a project called KIC out of Fermilab that's an open source FPGA. It's a system on chip from Xilinx that you can program with this open source software to do the different kind of controls that new labs that are getting set up in quantum computing might want to do. And your alternative is to buy these from instrument providers or startups that sell them at a bigger markup. There's other kinds of, anyway, there's a longer list. We wrote a white paper recently called Open Quantum Hardware, or maybe it's called Open Hardware and Quantum Technology. I think we just switched the title. And that goes through kind of a survey of the stuff that's happening there. And so I'm excited about more and more of the hardware itself becoming open. And there's even some projects where people are working together to make fully open sourced quantum computers. So like, here's your CAD files for the different parts to build the ion trap or the neutral atom trap. And like, here's where you can buy your component list to buy your lasers, and you can like build your own little quantum computer at home. It's not super, super cheap. We're not talking like it's a little more than a couple $1,000s, but it's a start that can help people with labs in other parts of the world get going. And one project that's doing that is called Open Quantum Design. They're spun out of the University of Waterloo.
Right.
So that's one trend. I'll mention another one, maybe I'll be a little bit more quicker, which is in compilers. There's a lot of different ways of making quantum computers. The story of the last couple of years is that there's not a convergence on a few technologies. There's actually a splitting of more technologies. And those technologies are getting more sophisticated. So there's capabilities for those quantum computers that are getting added to deal with error rates, make the error rates lower, that are more sophisticated. And so compilers need to get more sophisticated. And our compilers are pretty bad. So that's an area where we are doing quite a bit of work, and we're looking for more collaborators there. And then the third bit is our high-level programming languages are really bad, so we need better ones. So those would be kind of like open quantum hardware, compilers, and high-level programming languages.
So I feel like I could keep asking about many of the things that you said, but maybe it's a good moment to open it up a little more. And I was wondering if anybody has some comment or question that they want to ask.
Hey, this is Ash.
Hi.
So, guys, I mean, I'm not familiar with quantum mechanics apart from what I read in the paper and stuff that I read from other people. But is it where quantum computing is at? Like you kind of compare it to, say, nuclear fusion or something, where yes, on paper it's possible, but under very specific circumstances. Um, is quantum computing kind of beyond that stage? And now it's a question of just, hey, you know what, we've kind of got the guts and we've made it work. And now it's a question of kind of Moore's law type thing taking over and it becomes more efficient, faster, cheaper, and so on. Or are there still hurdles which are existing and you're kind of aware of them, and once those hurdles are done, then it can be sort of put into the technology sphere and just say, hey guys, have at it, like get this thing down to home computing level, or where kind of does it stand?
Sure. Yeah, I'll give you like a kind of zoomed out timeline. So back in 2015, roughly, there were no quantum computers.
Mhm.
And over the next few years, we got quantum computers, but they were really bad. Basically, all we could say about them is they are quantum computers. Like here's 2, 4, 10 quantum bits. You could simulate it by hand. It's not doing anything in terms of solving problems that's exciting, but they're quantum computers. They're entangled qubits. We control them the way we'd want to, that kind of thing. So that happened. Then what happened next is a few places started to demonstrate very esoteric benchmarks. They got quantum computers that were good enough to do benchmarks problems that they could solve with a quantum computer that they could at least argue that supercomputers couldn't solve. And the first experiment really like that was this called quantum supremacy experiment that Google did back in 2019. Then some people came back and said, oh, based on that, we were inspired and we came up with more clever classical algorithms for regular supercomputers. And so maybe we could kind of do it. And then and then a couple of years later, Google said, well, our quantum chip got a little better. We went from 54 qubits to 72 qubits, approximately. And now you definitely can't do it. And so the last few years, the story has been, it's always a little fuzzy, but it's saying, let's make quantum computers that are good enough to do something that regular supercomputers can't do. And that's a very, in this case, they're like kind of esoteric benchmarks. And so now what's going on is people are saying, well, now we can do something. We have enough qubits that, it's not obvious that a regular supercomputer can trivially simulate it. So we're doing something new. What can we do that's useful? And we know in the long term that when quantum computers get really quite a bit better, there are algorithms we can run that are useful, but there's kind of this gap. And so there's two things that are going on. People are trying to be more clever about the algorithms and applications and how they use them so that they work on worse and worse quantum computers. And then on the other direction, people are saying, what's the best quantum computer I can get my hands on? And let me see if I can make it useful make it do something for a problem that someone actually cares about. And so that's what's happening at the same time right now.
And just to follow up on that,
go ahead.
Is the sort of end goal, leaving aside the fact that we even need a quantum computer in our back pocket? So leave that aside. Is the end goal kind of, you see it, that quantum computers will be kind of replacing, effectively will be a cloud computing facility where people tap into? Or do you actually see them just like the old desktop computers that we have at home, or laptops or whatever, that is the level of technology will be deployed at? Or is it just going to be like, hey, you know what, replace the supercomputers and you've got like almost infinite, whatever, compute power in the cloud, and just use that for whatever you want?
Yeah. Well, I mean, it won't be quite that magic as infinite power. There's certain problems you can do a lot better, but not everything. But yeah, it'll be more like right now it looks like it'll first be deployments to data centers, supercomputer sized things, but internet and cloud is pervasive now. That doesn't mean it won't impact. Like maybe you'll be running an algorithm on a quantum computer every time you check your email that does some weird optimization thing. I'm not sure that's the first use case, but I don't think it needs to get to something that people carry around with them in order for it to impact how people live their lives every day.
I'll jump
Anybody?
up with a question.
Yeah, go ahead.
So, having gone through the trajectory up to now with classical computing, starting way back, like we mentioned with the transistors and everything, to where we are today, and having that as something to look at, how close is quantum computing's kind of trajectory to that? Obviously, since we've been through things, we can try and work on problems earlier. But where do you see kind of quantum computing's trajectory compared with classical?
It's a good question, and I get asked it a fair amount. You know, excuse me. I don't think the analogy is perfect. Like, there's a lot of things that happened in the history of classical computing that are different now. Like the first transistors all being bought by the military to be used in ICBMs before anybody thought about making computers out of them, really. Like, we don't quite have that circumstance now. And the second other really big difference is we have classical computing. And so when you were developing classical computing initially, you were competing against, human computers or slide rules. But also you didn't have a distribution system. And now for quantum computers, we can say things like, well, when they're ready, we'll put them on the cloud and everyone will be able to access them. And also we use classical computers to control quantum computers. There's this like hybrid thing that's really important to how things will get rolled out. And so though there are reasons that I don't think it's following the same path. Maybe another reason it's not following the same path is some of the technologies for building quantum computing that are most exciting are ones that leverage not just cloud infrastructure, but foundry infrastructure for making quantum technologies. And so they can scale really quickly if you can make them with existing foundry processes. And a lot of ones work with that. So there's silicon photonic stuff, there's silicon qubits that are close to CMOS. So there's kind of a complementary thing going on there. Now that said, certainly not at the PC era. Are we past the ENIAC era? Maybe. It's kind of hard to say. But one inflection point that definitely hasn't happened is there were a lot of ways of making classical computers for a while. There were analog computers in the 20s and 30s. There were a bunch of different weird memory modes with magnetic core memory, and like there were pneumatic things and proposals for using water pressure for memory. And then we got the planar process and transistors and then x86, and that kind of converged everything down. That convergence definitely hasn't happened in quantum computing yet. We're definitely before that, and it looks like it's going to be a while. And that convergence may still happen, but it's more of a multimodal time right now, which is fun and creative.
Hey, Will, I'm just wondering if you can talk a little bit about the high-level programming languages. You mentioned they were pretty terrible. So, like, what is the state of the art today? Is academia using the same thing as industry? And yeah, who are the primary players like driving the efforts there?
Yeah, so the main way quantum computers are programmed today is with barely domain-specific languages in Python, like Python libraries more than anything else. I built some of these and worked on some of these. They're mostly like builder pattern, like there's some instruction set representation. You use a Python program to construct that, and then you send it off. That's like the main programming model. That's not a programming language for quantum computing. And even with that, there's not really standard formats for the program that you send over the wire. There's not like a very clear instruction set architecture that everyone agrees on. There's a few projects that are working to make more standard instruction sets or intermediate representations. One is called OpenQASM, which has a few folks involved, IBM, AWS, different people. There's OpenQASM 2.0, and then there's an OpenQASM 3.0 that adds some more features. And there's another project called QIR, which stands for Quantum Intermediate Representation. And that's like a more LLVM compatible compiler toolchain. And one of the reasons these things are a little complicated is that you have to do classical computing with the quantum computing at the same time. So you kind of need classical compilation plus quantum compilation to all occur together. But those are just at the really low level. I'm talking like the equivalent of assembly, basically, would be a better analogy. So we don't have like a standard assembly yet. At the higher levels, there are some ideas. There's probably the most well built out software stack is called Q#, mostly built by Microsoft. It's like a multi-paradigm, like F#, like you kind of get functional patterns and object-oriented patterns in at the same time. And what to say about it? It has some advantages, but it's not like you feel like it's the end game for high-level quantum programming. There's another academic language called Silk, SILQ. There's a company called Horizon Quantum Computing. They have an interesting approach where they are making a compiler which, as much as possible, lets you write in normal C code and then just auto-magically behind the scenes compiles it into a quantum program that speeds up the parts that the quantum computer can do faster, which is in early stages, but is being developed. Yeah, I mean, I think there's a lot of room to do high-level quantum programming better, and I think it will unlock more applications because we'll have better tools to express the algorithms we want to express and figure out how to build them at bigger scale. And like just as an example of why this is important, quantum programming is very different from classical programming. You can't copy information in a quantum computer without paying attention. Like you can't write x equals 7, y equals x with two different variables. Like, you know, that program is dangerous from a quantum perspective. Depending on how you pass things around, is this thing called the no cloning theorem. You know, you can deal with parts of this, but you have to have like different kinds of data structures and different kind of programming models. And it remains for someone to, I think, come up with like a really elegant way of doing this. I could talk about this a lot more, but I'll stop there for right now.
I was wondering, maybe just a follow-up on that. I mean, you mentioned, of course, now we are still at a very early stage, and I'm not sure how it was. Maybe it was similar for classical computing at the beginning, but right now the feeling is that a language like that would be nowadays very hardware specific. Like it seems like there are, at least this is my impression, like there are big differences in how different hardware implement not just gates and stuff, but like later error correction protocols, etc. And so I wonder, to what extent do you think like it's actually going to converge, or it's actually potentially going to maybe converge into several very distinct languages?
I think there'll be different programming models. I still think there's a need and an opportunity to do high-level quantum programming. Like at the end of the day, they're all going to run unitary. They're running the same programs. Like they're running unitaries that run on qubits in some architecture. Yeah. And the point of it being high level is that like you're not really paying attention to like register allocation and which qubits have which errors and like what error correcting code is running. Like the code that is aware of that stuff, that's really hard to write right now without being super, super specific. But at the end of the day, we're going to run logical gates. And so I think you can build software in advance of big quantum computers. Now that said, there's other things, you know, there's these analog quantum computing systems that are coming along. So there's like particularly one of the ways of making quantum computers is to use neutral atoms, which is like a cloud of atoms that you catch in a laser trap. They're scaling pretty well, and they have an analog computing mode that you can operate them in too. And that's a different kind of program model. You can mix the digital and analog because you can also do the digital with it, and that would be a different kind of language. But even if we just restrict ourselves to digital quantum computing, like you know, it might not be the thing that gets advantage first because it's high. It's just like high level. Like the trade-off in high level is you get expressivity, but you lose performance. So we need both.
Yeah, I think I had in mind more maybe I was thinking more about the lower level stuff, like not the lowest level, but kind of intermediate. I'm currently
Yeah.
thinking a lot about error correction, and it seems all very intricate. It's like
Yeah,
almost
that
like you are
stuff's
wiring
super
by
interesting.
hand everything, you know?
Yeah, that stuff's all the compiler stuff at that level is super intricate. And I think that's why doing it in open source is going to be better. Otherwise, everybody's going to be just reinventing the wheel for their individual system. Like, yeah,
Yeah.
there are some things for your system that you've got to do really specifically. But then the stuff that's generic, like everybody should just learn from each other and then
Yeah.
like fork it or like make it like their
Yeah.
big version and then share what can be shared. That's my
Yeah,
hope.
I think it's interesting what you just said about like not everybody has to build their own stuff, because I think that currently the state of many companies and also in academia is that people come from academia, or many, at least the physicist side of it, and I feel like physicists always want to do things their own way. Like it's like, oh, there's a library, I'm just gonna do it myself and do it better. And like and I do sense that as the field progresses and things become more sophisticated, there will have to be a transition to something like that, to like tools that are, you know, improved by many, built by many, and like that actually grow in functionality and efficiency
Yeah, I
in a
mean, this
way
is a
that
part of
one
my
person cannot do it. Yeah.
Yeah, I mean, we're already there. It's just people with a little bit of denial. I think it was a story. So back in 2016, I was running the software group at a startup called Rigetti Computing. We were really the first. We were building superconducting quantum computers. IBM beat us to launch their stuff on the cloud by about, I don't know, 6 months or something like that. They just had their 8-year anniversary. Um, but they launched it with a GUI. So we were the first to really launch like a Python, one of these Python programming frameworks to program quantum computers, and we made it open source for a bunch of reasons. One was to help people validate it and understand it because it was new. And at the time, I was like, "Isn't this great? Like, we're like other people can just use this, and they won't have to reinvent a Python library that lets you create an instruction set architecture and send gates to quantum computers. Like, then people can just all work together and add on things, and it'll develop and build." And yeah, that's not what happened. Um, what happened is everybody built their own version. So then Google built a Python library that lets you build. It's exactly the same feature set called Circ. IBM made one called Qiskit, and then a few years later, AWS made one called Bracket. They're all the same thing. It's a Python library that wraps gates in some data structure. They've gotten a little bit more sophisticated since, but like there's different reasons that people don't work together that don't have to really do with features and technologies. And one of the reasons I think Unitary Fund is important is the stuff that we build can be adopted by more people, because we're not some competing company. Like, we're not trying to make money with it. It really is just a toolkit. If people take it and fork it and make their own version, like, we don't care. That's actually what we want. I mean, we do care, actually. That's what we want. So I'm hopeful that in the way we're structured, it'll encourage more people to be creative with what they build.
Hey, Will, I'm wondering if you can talk a little bit more about starting Unitary Fund, and especially like kind of the community building aspects. Like, how do you find other people who care about the same thing that you care about, get the word out, and how do you think about supporting projects with these grants?
Yeah, I would never underestimate the power of talking about things on the internet as a way to find people. So Unitary Fund started just like at the blog post that I did about almost 6 years ago now. So when we launched our toolkit at Rigetti, we started getting people on GitHub from the usual suspects, like, Harvard, Caltech, whatever. But also we got useful pull requests and bug reports from, hobby software engineers in Eastern Europe and Irish high school students and grad students in India. And I had seen some grant programs in other areas like machine learning, and had kind of seen how the open source toolkits in ML, like TensorFlow or PyTorch or ones before that, had like really accelerated the development of that field. And we thought, well, why don't we try and help make that happen more in our field? And so I I was working at a startup, so I had out of grad school, and I didn't have that much saved. So I took $6,000 and was like, "Here's some. We're gonna give out 3 grants, just as a trial," and launched a blog post. And then some other people jumped in and said, "Well, I'll fund some more grants," and then it sort of just snowballed from there. So I guess the answer is launched really lightweight, did some very small things that don't scale to prove that it was real, and then built things step by step from there.
And then do you think about like measuring success at all? Like how quantitative are you about the impact that you're making?
Yeah, there's a lot of ways you can look at it. So, we've had 2 startups, 1 big nonprofit, like 30 or something papers, dozens of people who now work full time in quantum technologies, whose first thing in quantum was a microgrant with us. I don't know exactly the numbers off the top of my head, but we track GitHub stars on all the projects. There's a bunch of open source projects and downloads and that kind of stuff. And with the occasion of our 100th grant, internally right now, we're actually doing a bit of a review for how we're going to talk about that impact. And so look for more to come in some more posts too. Do you have a question, Ryan?
Right. Yeah, Ryan.
Yeah, thanks. Just looping back to what you were saying before, William, as far as the open source stuff. I'm just curious what your thoughts are for like sustainability for a company to be able to build something sustainably open source. It's like we've seen in the AI space with like Stability AI coming strong out of the gates, and there's obviously a lot of problems with that, but struggling to find like to this day like a way to be able to monetize the product, something that you're putting out as open source. Second to that is that if you're a company, obviously, and taking on, let's say, venture capital funding in the beginning, then you obviously have this bias and pressure to monetize and all this kind of stuff, and how that affects like a product roadmap early on from the beginning. So I'm just curious what your perspective is for like, how do you see like new startups just building in this space to have a long-term vision and how to be able to sustain themselves, or even not even a startup, maybe it's a nonprofit, to be able to just continue to build and have sustainable funding, maybe without going the VC route, or all the dynamics that go into that. How do you see that like working out in the future?
Yeah, I mean, look, I think there's room for a lot of different ways of building new things. On open source, you definitely can build big businesses on it. I can't remember what Red Hat's acquisition price was, but it's pretty good. And there are different models around open. There's dual licensing. There's selling a service where open source is in the middle. There's selling services on top. But I think with all the different options, it's just worth knowing what you're trying to do. I'm a venture capitalist. I think venture can be really great for some things, but there are other businesses that don't fit the venture capital profile, right? And they can still be good businesses, and they can be really financially rewarding for everybody who works there and the people that founded it. You just get the issue is when you try and raise, or do even successfully raise, in the wrong model for what you're trying to do. That's where things get a little bit stuck. Like you end up maybe needing to grow in ways that you don't want to or shouldn't, or you're undercapitalized. That's the other side. Or you're a nonprofit that's realizing that it should be a for-profit, and you can fix that kind of as you go. But I think there's tons of room in quantum technologies, just like in regular technology, for all sorts of different organizations. You just need to be really clear about what you're trying to do and why, and then use the structure that you want to do that. And then one other thing I'll say is like, being creative about structure is not necessarily so worthwhile. There's corporation, nonprofit, venture backable startup. I would say like, here's a simple menu. Within one of those is probably what you want to do. And you can be tempted to do something really complicated, but that just makes it harder to sustain and fund, because then everybody's looking at some kind of weird product separate from weird investable product separate from what it's actually doing.
Thanks.
I have a bit of a self-serving question. I'm wondering what's your opinion about whether companies, like industry, should pursue open source? Like there seems to be a bit of difference between different companies. Like some, like Qiskit, for example, is very open. I don't know if it's not totally open now, but it's really very open. There are other companies that keep everything very closed. And in particular, I'm wondering about a startup that is just, trying to get a foot in the market, in the ecosystem, whether it's wise for them, even for them to be very open about what they're doing from the beginning, or whether it's maybe counterproductive.
It's hard to answer the question generically. Like it really,
Yeah.
like I think, like being open source is not, and I like at least I say this as someone who builds a lot of open source for ideological reasons. But like being open source is not an ideological decision, actually.
Yeah.
It comes from what your goal is. And you can have like very economic incentive returned goals that mean you open source something. For example, if you're making quantum computing hardware, it's a really hard thing to program. Why don't you make it as easy as possible to program this thing by just like putting it totally all out there and transparently at the accessible software layer? Like, don't make it even harder. Don't make me have to like read through proprietary docs to alter your high-level user software. Like, just make that really easy so that the part that you really know how to do and sell, which is your hardware, like I can get access to. So that is, I think, why most of the vendors that are making hardware, the like top level of what they're building is open source right now. That said, if your product is to license programming software for quantum computers, depending on how you want to get that funded and what the market's going to be, you might want that to be closed source. It sort of all depends on, and there's different pieces of it. Maybe some of it's open, maybe some of it's closed. You kind of have to make these decisions as like business and user decisions, sort of step by step. So there's not really a generic answer, but it's like a strategic question with in terms of whatever kind of company or nonprofit or research group you're trying to build.
Yeah. I'm asking because we are currently thinking about these kind of questions, like whether to release some part of our software. So right now we do simulations of quantum computers, but we're going to continue building different software for different parts. And I don't know, my view is that that first we need to make ourselves known, and then by giving first, and then we can start building on top of that and not be too closed in what we already have. But I'm not a business person, so so I'm not sure.
Yeah, I mean, look, like people in this field are very technical. Usually the users are very technical, and so they tend to really want to get under the hood at what's going on.
Yeah.
And by having the software be open source that they work with, that builds a lot of credibility with them, and it gives them a lot of flexibility for whatever bespoke thing they're trying to do. Because it's not like there's like everyone's doing the same thing. We just need to make it easy. Here's a black box that does it. It's like everyone's doing some kind of custom whatever, usually in quantum technology. And so having it be open source makes it more flexible for them to integrate it into whatever stack or workflow that they're using. This stuff's also hard. So like just saying like, here's the code, read it, ask questions is like very helpful at this stage.
Yeah. Does anybody have any questions? Or comments?
Will, maybe going back a bit, you were saying that kind of the math for quantum computers kind of imply they do math differently, so they don't work well with use x equals 7, y equals x kind of thing. Can you unpack that a little bit more? I'm just curious, like what's going on there?
Yeah, so like the fundamental model for what a quantum computer is doing is that you are multiplying matrices of complex numbers pretty quickly. So like you represent a quantum bit with two complex numbers, and the square of the first one, this says the probability that that bit is 0, and the square of the second number says the probability that that bit is 1. So with like a little image, like a normal bit is like a 0 here and a 1 here. A probabilistic bit, like a coin, is like somewhere on this unit line between 0 and 1, where like a fair coin is in the middle. And a quantum bit is some point on a unit sphere, where like the North Pole is 0, the South Pole is 1, and all along the equator are things that look like fair coins, but they're all different. There's like this other angle. And that other angle comes from, well, is modeled by using complex numbers to describe these. So we don't model them with probabilities, we model them with sort of square roots of probabilities that are called amplitudes, and that can be imaginary. And so each individual quantum bit is a vector of two complex numbers. And then when I have more of them, I tensor product those vectors together. So 2 quantum bits is 4 complex numbers. N quantum bits is n complex numbers. And then when I apply operations, I take that vector and I multiply it by a matrix of complex numbers. So every time step in a quantum computer, you take the state of the memory, so n qubits, like a 2 to the n qubit vector, and you multiply it by some 2 to the n by 2 to the n complex matrix. And like that's what happens every time step. And then you end the computation with this vector, and then you read it out with some other special operation called a measurement operation that turns the amplitudes, which are quantum information, into classical bits again with some probability that's described by squaring those complex numbers. So it's not Boolean logic, like Boolean, normally it's like I have zeros and ones, and I do ands and ors, and then I get zeros and ones at the end. It's I have these amplitudes, and I do these like matrix multiplications, and then I do this like measurement operation. It gets a little more sophisticated. You can do measurements in the middle and then make decisions and whatever, but that's like the high level thing that's going on. So it's not like mysterious secret magic math. Like it's complex linear algebra, but it's not Boolean circuits.
I think I got most of that. Thanks.
Yeah, and there's you can point, there's like on my website there's kind of like some links to lecture notes and some lectures where I've talked about this like a little bit more too, if that's useful. But yeah, there's kind of like higher level implications that come from it being from the underlying programming model having not Boolean circuit mathematics, but like complex linear algebra mathematics that have to do with these like no cloning. You can't like universally copy data around. Whenever you try and do this measurement operation, it changes the memory. Like this kind of like weird programming things that like emerge from that.
Hey, Will, can you speak to like the quantum materials that would go into creating a quantum bit, and like the ways that it's done now, and maybe ways that you're excited about that it could potentially be done in the future?
Yeah, so there's a lot of ways of making quantum bits. And one of the things about this field being exciting is over the last 20 years, every physicist who has a physical system has said, yeah, I also have a quantum bit in my weird way of doing things. So like for light, for example, basically you need anything that has a binary system that behaves quantum mechanically. So for photons, when they move through the air, they spin like a football. So left hand spin or right hand spin, that's 0 or 1, and you can make superpositions. Or you could have 2 different colors of photons. Or you could have what's called time bin encoding, which is like, imagine that time is split, well, it is split into seconds. And you're going to say, if the qubit arrives in the first half of a second interval, it's a 0. If it arrives in the second half of a second interval, it's a 1. And like that happens every clock step. So you can get so this time-bit encoding of qubits. You can have it be path encoded, like if it's going left, it's a 0. If it's going right, it's a 1. And then you have like a half sobered mirror that like splits the direction the photon goes. And that's just photons. You can also have like electrons in different orbitals. So like in the superposition between being in different orbitals. You can have superpositions between bits of matter. You can actually have these mechanical resonators that oscillate, and the frequency that they oscillate at, I can't remember how big people have gotten them, but we're talking like, I don't know, like hundreds of nanometers or something like that, I think. The frequency that little mechanical lever oscillates at can be in superposition, which means if you time it right, you can have this little lever be in a superposition of being down and up at the same time. You can have superconducting currents in a little loop that are going around left or right. I will just stop my listing now, but there's a lot of ways people have proposed to make qubits, some of which work better than others. One of them that I'm particularly excited about that I haven't mentioned yet are called silicon qubits. And so that's trapping an electron in silicon in a little hole. And electrons have a spin left or right. And if you trap that electron, then you can program it and have it spin either left or right. What's exciting about this technology, I actually invested in a company called Dirac. I'm wearing their t-shirt today, I just realized, that makes them, is that the way you make them is relatively close to regular chip technology, so regularly close to CMOS. So if we can get them working, then we can scale them out, and you could potentially have billions of qubits on a normal size chip. You have to keep it cold, but that's a pretty exciting direction for that reason. There's also ones in diamond that are kind of cool, but you can look that up later.
If nobody's jumping in, I thought I'd give you a chance also to talk maybe a bit about these microgrants that you mentioned. I'm curious about them. Yeah, so what are they? And I'm wondering, how does it work exactly? Like, is the idea that, you know, similar to startups, out of 100 microgrants, a couple of projects actually grow to become big, or what's the mindset behind it?
Yeah, it is more like we treat it kind of like a startup model where we don't expect everybody to succeed. We want to take some risks with what we fund. So we funded about 100 of them. Right now, they started as $2,000 grants. Now they're $4,000 grants each, so one size fits all. But sometimes people have come back and applied for multiple ones for their same project or the next iteration of that project. And we funded a lot of different kinds of things, everything from open source software for everything from high-level quantum programming languages that we've talked about, to application software, to educational materials or workshops. Like QWorld is a nonprofit that we give the initial funding to. They've done workshops for hundreds of people in like 20 countries. I think they've done hundreds of workshops in like 20 countries over the last couple of years, exposing people to quantum programming through notebooks and workshops and week-long courses. We've started to fund a little bit of open hardware. There's a lot of stuff in there. And so the structure is a pretty simple application. It's a couple minutes, a little video. And when we review it, we review them monthly. We look at a few things. So we look at, does this project match up with Unitary Fund's mission, which is to help create a quantum technology ecosystem that benefits the most people. So it's got to line up with our mission. 2 is, will our funding make a difference? So if you need to buy $1 million dilution refrigerator for your quantum computing company, our $4,000 probably isn't really going to matter, even if you're great and it's all going to work. But so that's not a great fit for us. And then thirdly, it's the people involved, because in addition to the projects themselves, we're really trying to help people get into the space. And the way it works is we give $2,000. If we accept a project, we give $2,000 up front. We check in halfway. When people apply, they save the duration of their project. They're usually between 2 and 6 months. We check in halfway, things are going well, we fund the second half, and at the end we help them get whatever their deliverable is out there or connected, and we use our network of advisors at Unitary Fund and the team and our partners to help the projects too.
Yeah, could you compare and contrast like the mindset differences between a quantum technology VC and like a traditional, what we typically might think of as a venture capitalist, like someone investing in, I don't know, enterprise software, right? Do you have like a longer time horizon? Are you, yeah, like how are things different? And also like maybe as a secondary question to this is like, where do you come in on the spectrum of this is my PhD thesis to we have something that we can go sell tomorrow, like in the commercialization spectrum?
Yeah, on the first one, I guess we don't have too weird of a structure. It's a standard VC fund structure, but it's a 10-year fund. I think the major difference is we're domain experts. So and there's different ways of being a sector-specific fund. You could be a cybersecurity focused fund, or like in some region, like in Asia, Asian cybersecurity company or something like that. But we just focus on this area, and I think that's really important for this area because it's new and because it's complicated. There's a deep scientific knowledge you need to know, and then you also need to know the ecosystem because the markets are developing in new areas. It's not just like you go and look at some BCG report that says like, here's how big the market is, or I can like look at how much the big tech companies are spending on it today and know how big the market is. The market's not there yet. So you need to actually have a view on where things are going and what's going to matter next. And for us to do that, we need to be pretty focused and specialized in these areas and to have been tracking it and to be involved in different ways. I mean, I've been in the field for 15 years. And my partners as well have been involved for a long time. So that's one difference in how we approach it. And it means that we can talk to people really early. We develop relationships with scientists years before they might start a company. And so I guess the difference between us and another VC is we're willing to do that work because it's in scope for us. I'm not distracted by like needing to go invest in some like fintech. Like this is what I'm focused on. And I think that's what's going to help us generate returns. You had a second question, which is about when we get involved. And I've alluded to that a little bit, like sometimes really early, but that doesn't mean we write checks really, really early. We're investing in things that can become big businesses. We write checks really early. We're pre-stage investors, so it might be your first check in. We often like to be that, but we don't want to fund R&D with venture capital dollars like science. Like you're not funding science. That said, we meet people who have interesting science things that might one day become a company, and we'll talk to them. Maybe we can help them get some funding, and maybe we pay attention, and then like maybe like we help develop that relationship, and eventually it becomes a company that we fund. But like a simple test for folks who are on the science side is like, what is your product? Why is someone going to buy it? And when are they going to buy it? Like that. It turns out that actually like narrows quite a lot of stuff down. Answering those questions is pretty tough because they're not questions that scientists answer. They're usually like, I'm developing this technology because it is new and novel, and here's when it's going to be new and novel. And you're like, people don't buy things just because they're new. So we talk to people before that.
I'm just curious. Yeah, is it hard to find a great scientific mind who is also like as commercially minded as you would like them to be for running a business? And often, maybe sometimes that's like a co-founder relationship.
Yeah, like sometimes you get
like what makes for a formidable team in like deep tech.
Yeah, exactly. Like the main thing there is that it's teams that build stuff. If one person would be too hard. But a lot of the way that we help early on too is by helping assemble teams of people who are not just scientists. We've done that in our portfolio for quite a bit, like Pascal and Qubit Pharmaceuticals and other companies. because a lot of the times the technology here is built by people who've been working in academia on it for a long time, which means they really know the tech. It also means they like haven't had a real job because they've been in academia for a while. No, I mean, I was in academia, I get it. And so it's an assembly thing, but it's very doable. An issue you run into is when people don't recognize where their limitations are and they aren't willing to work with other people and build out that team, and that's where things get stuck sometimes.
Thanks.
I'm wondering about, since we are talking about money and investing, there is sometimes this fear in the quantum community that a quantum winter is coming, that maybe there is too much hype and right now people are investing too much with inflated expectations, and that eventually we're going to see a very strong deflation. And so I was wondering, how do you see that?
Yeah, I'm not worried about that. At least I have a lot. When I talk to people about that, I want to mostly give them a little bit of perspective. Quantum computing and quantum technologies have gotten a lot more private investment in the last few years than they ever have before. Big growth. Private venture investment in quantum technologies over the last couple of years has been maybe $5 or $6 billion. That's a lot more than in all the history of time before. It's also a little more than the size of one investment into Anthropic, which is one AI company. Like we also spend $30 billion a year on potato chips in the US. So if you're just thinking about like humanity's allocation of what's important, my worry is not that there's too much being invested now. It's that there's a mismatch between the expectations, which are high, rightly so. It's a very big platform level set of technologies that could be a new industry, and they're becoming a new industry. My issue is that expectations are high, but we actually are not investing anywhere near enough to really make that happen. One fab, one foundry, the new Samsung foundry, I think, is $25 billion. Like quantum computing requires, depending on how you do it, like new fab technologies and new everything else, like all these other things. If we're only investing like $4 or $5 or $10 billion over a decade, like we're not going to get there. So the important thing is to keep showing milestones in progress, which there have been steady progress, and making that progress legible to other people so they can see that we're getting there. Does that make sense?
Yeah, for sure. Yeah.
I think there's enough.
Yeah.
There's definitely a lot more interest out there relative to the scale of impact that this can have that would fund this, as long as there continues to be real technological and business progress. And I think like things like quantum sensors, which are related technologies to quantum computers, they use similar things. They use similar workforce, control electronics. There's a lot of overlap. Those technologies are further along. They work. You can buy them. The question is like, what are the size, weights, and power, and what are the markets you can address? And then they're kind of more further along in the commercialization trajectory. If those things become more successful, then that'll catalyze positive investment in the whole sector, even for things that are more long-term, like big quantum computers.
Yeah, what I wonder is whether those timescales, whether the right expectations are being well, I guess you are on that side, actually. I mean, in your case, I'm sure about it, but like perhaps investors that are not very knowledgeable about quantum and so on, I wonder whether the right expectations are being conveyed to them. And the reason I ask is not so much because I have contact with them, because I don't, but more because sometimes one sees very inflated promises by some companies that end up being a little vague enough that you can kind of find your way around it. But sometimes it does sound like like return of investment is just around the corner, and it's for quantum computing specifically.
Yeah, I mean, some people said, look, pick any area of commerce, and people say things that are not back upable by. I mean, I don't know, when we're supposed to get self-driving cars from Tesla, 2017.
Yeah.
I mean, pick any, and I'm not, I don't think that really serves anyone too much, but like our goal as an industry is not to have, like, the goal is not that no reporter shall ever write a story that is not with a crazy headline that we don't meet. Like, if we did that as the goal, we would make no progress and promise no progress and get no one excited about anything. Like, that's the wrong goal. The goal is to make progress. And sometimes that means that like journalists are going to misinterpret things and write crazy headlines. It means that like there will be frauds. Like people will see this as an exciting area and try and, you know, make up something that doesn't really work and try and convince people to invest in it. That's gonna happen. But that's not going to be what most people invest in. Like there are sophisticated investors who invest in serious, risky technologies all the time. And I think sometimes people on the science side don't understand very much about the business and investing world. And they don't really know how decisions are made there, because it's very different than how grants work in science, and it's very different than how labs work. And so they see things like what to them looks like a large amount of money into something that they personally wouldn't have invested in and say, oh no, people are being duped. And it's like, no, they just have like a very different risk profile than you. Like they're thinking about this very differently. And also we're very early as an industry. So I guess my summary is like, I'm not too worried about it. When I zoom out, I see there's been increases in funding, which is appropriate, but needs to continue to increase if we're going to do what we really want to say we're going to do. And that the funding is broadly getting allocated to real projects that are making real progress. Like we're like way further along. Like when I finished my PhD in 2015, I went to a garden party that my professor threw. And I told everybody there that I wasn't going to go to a postdoc. I was going to join a quantum computing startup. And they were like, what? That even exist? Like, you're going to work at D-Wave? And I was like, no. It's a new one. And I go back and look at a photo of that dinner party, and there's like 30 people there. And somewhere between 50 and 60% of them now work at quantum technology companies. Like at that time, they were like, yeah, there's just no way any of this is going to happen, that anything's going to get invested in, that anything could get built, and things move quicker than people expect. And I think that's going to continue to happen.
Will, how would you go about starting an open source like research and development lab today? If you had ideas, stuff that you've been personally researching, how would you go about starting a lab today with all the different options you were mentioning before? How would you personally do it?
Well, I got a lab today. Now I get to work at the Unitary Fund one. I think if you're doing, again, you should ask yourself what you're doing. If you are doing pure scientific research where you want to be judged on your contribution to knowledge in the open, it should probably be a nonprofit. Or an alternative structure is you do it as a for-profit and you get investors or funders who just don't care about ever making any profit. You should be clear about that. It's just that's sort of like a legal and structural question. An alternative is, you could start a contract research group where, there's lots of interesting questions that people want researched or answered, and you could be a researcher for hire. And that could be a small business, be a consulting business. There's versions of that in quantum computing where people pay money for people to do algorithm and application research and how you might use a quantum computer for X problem. That's not usually a venture fundable structure, but it could be a good small business. So I guess my answer is depends on exactly what you want to do. If it's really fundamental new research, I'd be encouraging. And I'd be encouraging because the organizations today that do fundamental, like science for science, knowledge for knowledge research are universities. And they're pretty high overhead incumbents. Like you can build new organizations that move faster and are more dedicated for that. Like universities aren't exactly in some ways often set up to do research super well. As an example, they're instead educational institutions. So if you look at a research lab that's trying to push the cutting edge of what they're building, it's often staffed by people who by definition don't know what they're doing because they're students. There's a lot to be said for the mentorship and apprenticeship model for training and science and knowledge transfer. And there's things that are good about that, but like you end up with grad students programming FPGAs, like reading the FPGA manual, when it turns out like you can hire someone who's like programmed FPGAs for 10 years and like they'll probably build it faster and cheaper and better. But universities don't do that kind of thing, and they're not set up to do that kind of thing. So you can start your own. There's actually a pretty cool kind of organization that some folks I know have been advocating for and building versions of for a while called focused research organizations. There's a group called Convergent Research that helps get those built. And you can think of those like startups, but whose goal is not to produce an exit or a return in like 5 or 7 years. It's to develop some technological capability that they're gonna open source and give out. So think of like the Human Genome Project would have been a good example of something that's like a good focused research organization. Like you run it like a startup, it's got a CEO, they hire engineers who know what they're doing. But the output is not, here's our IPO. The output is like, here's this big contribution to science that we've been able to do.
Can I ask a follow-up to that too?
Of course.
It seems like you're like a Renaissance man. You have like multimodal creativity, different, like all the hats you wear. How do you go down that path, like your day to day of being productive and doing the research, but also being the VC, but also being in this and also doing this? How do you like stay focused and achieving the things that you want to do creatively without like spinning too many plates at the same time and not getting anything done? I'm just curious.
Yeah. I mean, in some ways it seems like I'm doing different things.
That's my problem. That's what I want to know.
No, I get it. Well, I have one thing is that I'm not actually doing different things. I'm doing the same thing. Like I'm trying to help make quantum technology happen. I'm just doing it in different avenues. And so that means that I've been in the same space for a long time. And so I have a lot of context and networks that come from that. When I'm looking in new areas, like I really have to read the whole archive paper, not just like look at who wrote it, skim the abstract and skim the figures and like know if it's real or not. Like I can do that in my field, but in new ones, I gotta like really take the time to read it. So that's one thing that makes it work. And the second is yeah, it's building teams of people. Like our team at Unitary Fund does all of this. I mean, they're talking about all of their work now, really. And when it comes to investing, it's like, yeah, I'm investing in other people who are doing this work. Like I'm really helping support them. I get to talk about what I do know about the stuff that they're building. But like a lot of what I've used as a yardstick as I've made decisions about what to do with my career is like, how high leverage is this? And usually, and basically always, that leverage is through other people. So how can I be in positions where, I mean, in some ways I just like, I give away money, not give away, but like to people who are not going to make money, I give them micro grants. To people who can return the money, I can give investment. And so I spend a lot of time trying to find people. And so I'd say if you want to be involved in a lot of things, then other people are probably the ones who are going to do those things. So you should probably get really good at finding other people who are great.
Cool. Thank you.
So it's really cool questions. I just want to be mindful of the time. I don't mind at all staying longer, but in principle,
actually, I can take maybe like one more, but yeah, sorry.
Yeah, so that's why I wanted to. So okay, please, if anybody has something that wants to get out of his chest, this is the chance.
All right, cool. Well, we have microgrants at unitary.fund. If you have anybody who's interested in getting into the space, wants to get involved, we do hackathons too. We've got a hackathon called Unitary Hack that's coming up. It's really cool. We put bounties on open source software, and if you come and close those bounties, you get paid. It's a great way to get involved. So yeah, if you know folks interested, share that around.
Awesome. Well, thank you so much, Will. You were amazing in your answers. I'm learning new things also.
Don't set the bar that low. I mean, it should be that. I hope so.
Thank you guys both. It was great. Great
Yeah,
conversation.
great to meet you all.
And thanks for the